Hello folks. Okay, this time I want to get into talking a little bit about compilers and compilation in a little bit more detail. The idea of compiling programs that are spread across multiple different files, how we link all those pieces together to create something that can actually execute, and we'll go through and use C++ and maybe the G++ compiler as our example as we're walking through this process. So, we talked earlier about the idea that compilers are simply programs, just a chunk of software that reads a file, collection of source code written in a high-level language and translates it into something else. Potentially it could translate it into another high-level language, we can talk about that later, or it can translate it into assembly language, or it can translate it directly to machine code, the binary instructions that the machine would actually run off of. So our compiler is just a program that acts as a translator. And again, interpreters we mentioned earlier, same sort of idea. They're programs that read instructions written in a high-level language and then translate them into something executable and runs them, but essentially reads an instruction, translates it, executes it, reads an instruction, translates it, executes it, rather than the notion of a compiler where we read and translate an entire file or maybe an entire program and then execute the entire thing. So, subtle difference, but they do have a lot of the same behavior, a lot of the same issues to address. Not all, but some. All right, so we're interested specifically in the idea of the compiler. So again, if we want to think about what a compiler is doing, I want to run through a typical sequence of actions that the compiler might run through when it's processing your code. So first it's got to read the source code, and typically the first thing it's going to do is put it into some sort of standardized format. So it might replace all of the chunks of white space with just a single space or something along those lines. Standardize the white space. It might do something like stripping out the comments, right? Just some basic steps in advance to get everything into one nice standard format it can work from. Now, most compilers support some form of pre-processing, extra instructions that can be inserted in the source code telling the compiler, before you compile, I need you to do this, that, and the other thing. So we'll talk about some of these, but they include things like the hash includes, where it's saying, go off and grab this library or this other file and essentially cut and paste the information here. So there might be a bunch of instructions for the compiler on things to do before it begins the actual translation. Once it's gone through those preprocessor instructions, then it's going to say, okay, let me go through the chunk of code that I've got here and turn all of the different pieces in it into a bunch of tokens. So it might go through, this might be looking at all the different keywords, it might be looking at the identifiers, it might be looking at the punctuation, things like brackets and whatnot, and it's just going to go through your code and say, okay, this consists of the keyword void followed by an identifier for a function name, followed by an open bracket, followed by a whatever. So it's just going to go through and identify the sequence of pieces that you've got in your code at the most basic level. So once it's got this list of symbols, this list of tokens, it's going to go through and do some basic checks to make sure that the syntax is correct. Ooh, do I get a bonus for misspelling correctness? Okay, it's going to go through this list of symbols that you've got, make sure that it's just syntactically valid. Under the rules of the language, is this a valid sequence of symbols? And then it's going to go through and build what we'll call a symbol table, just a record of, for every one of these symbols, there might be extra information we want to keep track of. If I say that, okay, I found, the third thing I found in the file was an identifier. So I'm going to record that this is an identifier. I'll record the string that it actually represents, so maybe the string X or foo or something like that. And then there might be additional information to associate with it. So if this is a symbol for variable, then I might record the fact, okay, this is a variable, it's named foo, maybe it's got a data type associated with it, maybe it's got a value associated with it. So the symbol table is just keeping track, letting the compiler keep track of the symbols that are out there and what information it's got about them so far. And again, this is going to be useful when it's going through and trying to turn your code into machine code, for instance. So it'll go through, analyze these symbols, and then it'll say, okay, now I've got all this extra information, let's build, if you like, an intermediate version of the code. So we'll build a version of the code that's got some kind of internal representation of all these pieces. Then we'll go through and say, okay, now that we've got this internal representation that's kind of separate from the original high-level code, then we'll do any optimization that we can, and then we'll go through and generate the target code that we want to represent. So once I've got this intermediate format, I can say, okay, now let's turn this into machine code or turn this into assembly language or whatever it might be. So the compiler is going to be going through this sequence of steps. And of course, there's a lot that takes place in building the symbol table and in checking for syntactic correctness and in generating the target code and that kind of thing. But we'll leave that for another course another day. So again, the symbol table contains the information about all the different classes that you've got. Oh, geez, I misspelled classes too. All the different classes, functions, methods, data types, constants, right? Anything that you essentially defined as part of the code, it's probably got an entry in the symbol table somewhere. Or symbol tables, you know, maybe it's got one for variables and one for constants, or maybe it's got one for functions and one for classes, or who knows what. But you might have a variety of different tables or different pieces in your table. So when it's going through the code processing it, whenever it encounters, you know, foo or some symbol, it looks back to the table to see, okay, you know, what is foo? And is it being used appropriately at this point in the code? So this symbol table is typically kept in memory as the compiler is running, but once the compiler is done translating your code into whatever the target language is, you know, assembly language or machine code or whatever it might be, it doesn't need that symbol table anymore, right? It's completed the translation, that information isn't necessary, so it's dropped. So that kind of information doesn't get stored with the compiled code, which is one of the reasons that, you know, if you go through and try and use debuggers on code, they need the information from the symbol table to be able to debug the executable suitably. Right? The executable by itself doesn't have information like x is an int, you know, x was, you know, 32 bytes, it's got this string associated with it, whatever. That information is not stored in the executable. Right? The executable is only worried about what has to happen during execution, so it doesn't need all that meta information. But a debugger would need that information, which is why we'll come back and look at the idea that when we're compiling something to debug, we'll actually ask the compiler, oh, by the way, when you compile this, could you drop a copy of the symbol table in with the executable so that the debugger has that information available to work with? So, all sorts of fun and wonderful things. All right, when the compiler is actually going through translating something, right, the easiest case is where you've got a program where everything for the entire program is in that one file. Right? Everything that you use in the file is defined in it. Any functions you call are defined there. Any data types you use are defined there. So the compiler can go through, translate that one file, and knows it's got everything necessary to build the executable. You know, in that case, we can use a typical idea of just say, okay, please translate this program and build an executable from it. So again, for our if we're using C++ and the G++ compiler, then we might use G++, say here's the program to translate, prog.cpp's got the source code in it, and then say this is what I want you to call the executable, so maybe the -o and progx. And so somebody, assuming that there's no errors, somebody will then be able to go off and run progx and get the behavior they want. So that's the simplest case. It's not the general case. With most programs, they're going to be split across multiple files. So maybe we've got the definition of a class in one file, we've got the definition of another class in another file, we've got a bunch of functions defined in some other file, and then we've got some program that uses all of them. So you've got these 4 different files, and they're kind of cross-referencing between one another. So if we wanted to compile that, either we could say, well, let's give the compiler all of the files and essentially tell it everything you need is in here somewhere, compile all the pieces and join them together somehow. or we need a way to be able to compile them one at a time individually without the other ones present, if you like, and then have a separate step at the end that says, okay, take these separately compiled pieces and link them together to form an executable. And that is the far more common approach to use, but it's got some challenges associated with it. And that's what we want to take a look at next. So let's take a very simple case. Let's say we've got a function that's defined in one file and a program that calls it in another file. So we've got prog.cpp has the program in it, the main routine, whatever it might be, and it calls function foo, and functions.cpp or something like that has got the definition of our function in it. So we run the compiler on prog.cpp, and it translates it into a bunch of object code, a bunch of machine code, and somewhere in there is the call to foo. And then we run the compiler on this funcs.cpp file. It produces another file of machine code, of object code, and somewhere in there is the body of foo, the implementation of foo. And then we link the two of them together to form the executable. So in the case of the G++ compiler, if you're using an IDE, lots of IDEs will automate this process for you, but we'll look at what happens if we're going to do it manually first. So if we're using the G++ compiler, this -c flag is what tells the compiler that this is not a complete program that you're translating. It's just one file. I want you to produce the object code for this one file. So G++, this -c flag to say, okay, we're just doing a part of a program in this, the file that we're going to translate, and again the -o and what we want to call the translated file, the object code file. So usually we'll use this .o extension to indicate that it's object code. So -o, say funcs.o. And by default, if you use the -c and blah.cpp, it'll call the function or the program, the file that it generates in blah.o. But we'll do it explicitly here just because that's going to be useful for us later on. So we go through and compile the two files individually, funcs.cpp into funcs.o and prog.cpp into prog.o. And then we tell the compiler, okay, now I want you to link those two things together. So again, it's just G++, the two .o files, and what we want to call the executable, so -o progx. So with those three things, we can compile the two files individually and then link them together to create an executable. And what's useful about this is that if we've got hundreds of different files to compile and we edit one of them, I don't want to have to recompile all of them. I just want to recompile that one and then relink them. And so that's where this is leading. Now, we have a problem here though. We've got the code for foo in one file and the call to it in another file. The compiler is supposed to be able to check to make sure that the call is valid for foo, but it doesn't know anything about foo because it doesn't have that file when it's compiling prog.cpp. So one of the ideas is to have some sort of a coordinating file that says, this is what a call to foo looks like. Or here's the, if you like, the header for foo. So it would give you the return type, the name of the function, and the parameter types it expects, and the order it expects them in. And it acts kind of as a contract between the file that has the implementation of foo and the file that uses foo. So if the implementation file follows the rules in the header file, then it implements foo correctly. And if the file that's calling foo follows the rules in the header file, then it's calling foo correctly. So it gives us this kind of contract between the two. I'll build that, following the rules in the header file. You call it following the rules in the header file. So we'll typically use the .h extension to indicate that something's a header file. And again, this is the way that we'll link things together. And in the two files, they'll each specify, let's say we put the header for foo in funcs.h, then in the file that implements foo, we'll include the header file, so the compiler can say, does the implementation match what the header file says it's supposed to? And in prog.cpp that uses foo will include funcs.h. So again, the compiler can cross-check. Does the call in prog.cpp match the definition in funcs.h? So this is the contract system that we'll use, all based around the idea of header files. So again, they act like a contract between whoever supplies something and whoever uses it. One file does the implementation, the other one uses it. So the compiler can do its error checking when it does the two separate compilations, right? It can make sure that you're obeying the rules in the header, right? That the implementation obeys the rules in the header when it compiles that one, and it can make sure that the call obeys the rules in the header when it's checking the implementation, checking the prog.o, for instance, the prog.cpp. So the compiler can do the separate compilation on them, do the error checking there, and we can be reasonably confident then that when we link the two together, the call and the implementation will match, right? They both adhere to the rules we said we had to adhere to, so they should both link up correctly. And that's what we were aiming for. So in terms of a C++ example, the way this might look is in our funcs.cpp, we hash include, and this is an example of one of those preprocessor instructions, telling the compiler something that it has to do before it starts compiling. And again, the hash include is basically saying go off and grab the contents of this file. So in funcs.cpp, where we implement foo, right, we have the implementation and something that says, okay, go off and include that. And in that funcs.h, it's just going to have the profile for foo. It's going to say, okay, foo, returns an int, it's named foo, and it expects one integer parameter. And so when the compiler compiles funcs.cpp, it can check that the implementation of foo matches that header. And then the similar idea in prog.cpp, we hash include the header, saying, okay, go off and grab the header just to make sure that things match when we go through the rest of this code. And the compiler goes through, translates this code, sees the call to foo, and checks that it's valid against what the header says. So we can compile these two files individually and then link them together, and everything should work. So again, same basic idea, right? This is looking at the same sort of instructions as we had earlier. We do our G++ on the two individual files with the -c flag, compile this one separately, compile that one separately, and then our G++ command to link the two of them together, and then run the beastie. And that should actually work, as long as we followed the rules in the header file. So that's the notion of separate compilation. And again, the big advantage for us is that if we come back and we edit one of those CPP files, we have to recompile that one, obviously, because its code has changed, but we don't have to recompile the other one. Right? If I change the program that calls foo, I don't need to go recompile funcs.cpp because nothing's changed about the implementation of foo. Or if I change the implementation of foo, I don't have to recompile the program, right? Nothing in the program has changed, it's just the code inside foo has changed. So if we've got, it's not such a huge deal if we've just got 2 files, but if we've got 10 files or 100 files or 1,000 files that are all getting compiled, if we edit one of them, we don't want to have to recompile all 1,000 files. We want to recompile that one and just link them together again. And again, compilation for big programs with lots of files can be a lengthy process. So being able to recompile just the pieces that we need to can save you a lot of time. So, again, basic idea, edit a file, recompile that one, link them back together. Now, if we edit the header file, it's a little bit different, right? The header file might have definitions that are used by both of the other files. So if we change it, then we really need to recompile both of the other files to make sure that they both conform with the new definitions in the header file. So we do have to be a little bit careful about what we recompile based on what got edited. Now, we can wind up with a fairly complex collection of header files and .cpp files, and if we edit something, we want to make sure that we just recompile exactly the right things. Anything that needs to be recompiled does get recompiled, but anything that doesn't need to be recompiled doesn't. Right? We want to kind of optimize our performance here. So typically what will happen is we want some means of automating this process. And it's really tedious to go through and manually figure out, okay, I edited this one file, what do I need to recompile? So most software development tools, most IDEs will automate this process for us. We'll take a look at what has to happen, how we can figure out what things need to be rebuilt. And we'll take a look at a technique that we can use called makefiles, where we can create a set of rules that says, if this file gets modified, these other things need to be rebuilt. Or more specifically, if I want to rebuild this thing, what files does it depend on? Rebuild X if any of the following has changed. And so what we're going to do in the next stretch is start building up this hierarchy of recompilation rules and instructions on how to rebuild any individual piece of our, or any individual part of our executable, including all of the different object files that it might make use of. So this is the process we're going to go through with next. The notion of a makefile is just a collection of rules that says, if you want to rebuild this, here's the things to check. Under any of the following circumstances, rebuild it. Here's the instruction to rebuild it. So in our project, you used make demo, for instance, to rebuild the demo program. That's following this exact idea, where you type in make something that you want to update, and the make program goes through your make file and goes through the modification dates for all your files and figures out what's been edited since the last time you rebuilt things, and therefore what needs to be rebuilt. So we'll go through all of the fun and joy of that in the next couple of sessions. Now, in C and C++, we talked about the idea of the .h extension for our header files. So some of the things that we're going to look at in our next stretch are the things that we have to do to make sure that this all functions correctly. So some of the preprocessor commands that we have to worry about. So things like having the hash includes in there, things like trying to ensure that something doesn't get included multiple times and we don't try and recompile something multiple times if necessary. So we're going to go through this process in a bit of detail in our next session. But the hash include is the most basic one to get started with, and it essentially amounts to a preprocessor instruction telling the compiler, go off, grab the contents of this file, and dump it here before you compile. So we'll pick up with more of the joys of the compilation process next time around.